This week we're going to be looking at eigenvalues and eigenvectors. These are special vectors and special numbers that are associated with a matrix and tell you a lot about its structure. Eigen is German for special or characteristic, so eigenvalues are special values or special numbers that are associated with a matrix, and eigenvectors are special vectors that are characteristic of the matrix and tell you a lot about its structure. This will just be introduced with an example before we get on to the general theory. So here I am considering a 2 by 2 matrix. It's the matrix 4, 2, 1, 3. And associated with that is a linear transformation, for which this is the matrix that represents it. So the linear transformation is vector x in the plane maps into a new vector which is equal to a times x. So for example, if the input vector is 1, 0, then the output vector is 1 times the first column of A plus 0 times the second column of A, so that's just the first column of A, which is 4, 1. So here we see the blue input vector and the red output vector. Let's try some other input vectors. Well, 2, 0. 2, 0 maps into twice the first column of A, so that's 8, 2. What about 0, 1? 0, 1 maps into the second column of A, that's 2, 3. Here it is here, 2 along and 3 up. So when I swing around the vector x, I can make it longer or shorter, change its angle. The transformation does different things, and you can see already that this is going to be quite a complicated linear transformation. This is not going to be just a simple scaling or rotation or reflection, as we considered earlier. It's doing a whole combination of those things. And we'd like to understand what actually it is doing. You can see that both the length and the angle between x and x prime is changing as I move the input vector x. So one way to simplify this is to look for special input vectors x such that the angle doesn't change. In other words, such that x prime lies in the same direction as x. And if I just move x around, I can see that there will be such directions. So here's one at, let's see if I can line it up exactly. Yeah, there we are. If x is equal to 1, 0.5, then x prime, that is 1 times the first column plus a half times the second column, that's 5, 2.5. It's exactly 5 times x. So for this input vector x, all the transformation does is scale its length by a factor of 5. If I move to 2, 1, again, the linear transformation just scales x by a factor of 5. So this direction, any vector in the direction 2, 1, will be an eigenvector. It's a special direction such that in that direction the linear transformation does not alter the direction of x, it just simply scales its length. It simplifies the transformation. Are there any other special directions for this matrix? Well, we can hunt around experimentally for them. No. Ah, yes, there's one in here. It's at minus 1, 1. If x is in the direction minus 1, 1, then x prime is minus the first row plus the second row, it's minus 2, 2. Sorry, minus the first column plus the second column of A. That comes out to be minus 2, 2. So again, in this direction, the linear transformation simply scales x, this time by a factor of 2. Are there any more special directions? Well, you can hunt around. There's one down here, but that's just the negative of the one I had before. There's another one over here. That is the negative of the one I had before. There's basically 2 special directions. Let's see if I can go back to 1. Let's go to 2, 1. That's a little bit easier. There we go. So that is one of my eigenvectors, 2, 1. And now the question is, how would you find that algebraically? For example, if you were in more dimensions, if you had a 5 by 5 matrix, of course you couldn't simply draw the vectors or try all possible vectors until you found them. We need a more systematic approach. That's what's happening over here. I'm looking for special vectors x such that a times x is proportional to x. In other words, some scalar multiple of x. I don't know yet what the scalar multiple is, so I've called it an unknown variable lambda. That's a Greek letter. So now I want to solve this equation for x and for lambda. So this is actually a system of nonlinear equations. It's more complicated than the simple linear equations we had before, ax equals b, because I've got this extra unknown here, and I have two unknowns, lambda and x, multiplied together. How can I solve these equations? Well, let's start by moving everything onto the left-hand side. That's a fairly traditional step. And now I see what might be a good idea would be to factor out this x, because I appear to have a common factor x in both terms. But you have to remember that these are systems of equations here. If I wrote this all out for an n by n matrix, it would be a very large system of coupled equations. So I have to be careful with the matrix algebra. What I will do is replace lambda x by lambda times I times x, because the identity matrix times x is equal to x, so these two lines are the same. And the reason for doing that is that now I have matrix times x here, and also matrix times x here, which means I can now factor out x on the right. Because if you check this, how would you expand this out? You'd get a times x minus lambda times I times x. You'd get the previous line. What's the next step? Now I've got a matrix times x equal to 0. Well, one solution would be x equals 0, but that's called the trivial solution. I don't want that solution because that would be a solution for all values of lambda and for all matrices A. That's really not very interesting at all. So I want a non-zero solution for x. And here is where you have to remember the fundamental theorem of invertible matrices. A matrix times a vector equals 0 has a non-zero solution x if and only if the matrix is non-invertible. So I want to choose lambda that makes this matrix non-invertible. That means that matrix must have 0 determinant. That's a very powerful theorem because I've actually got rid of almost all of my unknowns x. Instead of n equations and n plus 1 unknowns, I now have one equation and one unknown lambda. That's much simpler. Let's try that in this example. A minus lambda I, well, the matrix A was 4, 2, 1, 3. Minus lambda I, that means subtract lambda from the diagonal. Take the determinant. That's 4 minus lambda times 3 minus lambda minus 1 times 2. Expand that out, you get a quadratic. You get lambda squared minus 7 lambda plus 10. That's just lambda minus 2, lambda minus 5 equals 0. So there will be two solutions. There lambda equals 2 and lambda equals 5. If you remember the interactive demo a few seconds ago, we found that in this example, this input x was scaled by a factor of 5. Lambda 2 is 5. The other input vector over here, the other special one, was scaled by a factor 2. That's lambda 1 equals 2. How do I find the eigenvectors? Once I know the lambdas, then it's easy to find the eigenvectors because I plug them back into this equation here. I know the value of lambda, so I know this matrix. I have to plug in here and solve for x. So there'll be one eigenvector that goes with this eigenvalue and a different eigenvector that goes with the other eigenvalue. I think these are written down here. Here they are. So 2, 2, that's this one, or any scalar multiple, and 2, 1 is the one I found before. Now all of this here, this is not special to 2 by 2 matrices or to this example. All of this works in general for any matrix of any size. This is very powerful. This shows the power of all of these tools that we've been building up over the previous weeks. I mentioned the fundamental theorem of invertible matrices that was used to get from here to here. But there's something else going on here too. Suppose A was an n by n matrix. Well, if you take an n by n matrix and put minus lambda, subtract lambda from the diagonal and work out its determinant, you'll get a polynomial of degree n. In this case, I got a polynomial of degree 2 because I had a 2 by 2 matrix. With an n by n matrix, you will get a polynomial of degree n. You're setting it equal to 0 and solving for lambda. That means you're looking for the roots. The fundamental theorem of algebra says every polynomial of degree n has exactly n roots. That means that every n by n matrix has exactly n eigenvalues. So there will always be these special numbers, these eigenvalues associated with every square matrix. Each eigenvalue will have an eigenvector that goes with it. They're the special directions. That's more or less the theoretical content for this whole topic on eigenvalues and eigenvectors. There's a few little bells and whistles that we'll come to. Mostly what we have to do, though, is do some more examples, see how this works in practice. How do you find the lambdas? How do you find the x's? And what do you do with them when you've got them?